Hey everyone, tonight we're journeying into the heart of stellar serenity. Before we begin, take a moment to like this if these cosmic explorations bring you peace, and share in the comments where you're listening from and what time it is in your corner of the world. I'm always moved by how our global community comes together to contemplate the infinite together. Now settle back, dim those lights, and let your breathing slow. Tonight, we're not seeking cosmic drama or stellar explosions. Instead, we're going to explore something far more profound and deeply peaceful, the gentle, billion-year dance of nuclear fusion that sustains main sequence stars in perfect balance. Let's begin our meditative journey into the patient heart of stellar existence. Imagine, if you will, this very moment as dawn breaks somewhere on Earth. The light touching your world has traveled 93 million miles from the surface of our nearest star, carrying with it the patient energy of nuclear fusion that has burned steadily for over 4 billion years. This is the light of a main sequence star, our Sun, locked in the most serene cosmic dance imaginable, the perfect balance between gravity's inward embrace and fusion's gentle outward pressure. Tonight, we'll explore this exquisite equilibrium that governs the longest phase of stellar life. We'll journey deep into stellar cores where hydrogen atoms slowly, patiently transform into helium across timescales that dwarf human civilization. We'll contemplate the profound stability that has allowed this nuclear furnace to burn with such constancy that life itself has had time to emerge, evolve, and contemplate its stellar benefactor. In the vast cosmic theater, main sequence stars are the universe's great meditators, burning with quiet consistency for billions upon billions of years. They are cosmic lighthouses of stability in an ever-changing cosmos, their gentle fusion fires providing the steady energy that makes planets habitable and life possible. From the smallest red dwarf stars that will burn for trillions of years to massive blue giants that shine brilliantly for mere millions, we'll explore how stellar mass determines not just brightness, but the very rhythm of cosmic time itself. Prepare to drift into the patient timescales of stellar evolution, where a single stellar lifetime spans thousands of human civilizations, and where the gentle nuclear alchemy occurring in stellar cores connects us to the very atoms that make up our bodies. Let the cosmic vastness wash over you as we explore the serene physics of stellar equilibrium. In the vast cathedral of space, where silence reigns supreme and time moves with the patience of eternity itself, main sequence stars perform their most profound and enduring act of cosmic balance. These stellar giants, including our own Sun, exist in a state of perfect equilibrium that has persisted for billions of years, their cores burning with nuclear fires that dance in exquisite harmony with the relentless pull of gravity. Picture, if you will, the invisible architecture that governs every main sequence star, a delicate scaffolding of pressure and temperature that extends from the blazing core to the gentle photosphere that radiates light into the cosmic void. This is hydrostatic equilibrium, the fundamental principle that allows stars to maintain their shape and size across eons that dwarf human comprehension. Deep within the stellar interior, the outward pressure generated by nuclear fusion pushes against the inward crush of gravity with such precise balance that the star neither collapses nor explodes, but simply continues its patient burn across geological ages. The journey toward understanding this stellar equilibrium began in the early 20th century, when the brilliant astrophysicist Arthur Eddington first glimpsed the mathematical beauty underlying stellar structure. Working in the 1920s, Eddington developed the fundamental equations that describe how pressure, temperature, and density vary throughout a star's interior. His work revealed that stars are not solid objects, but rather vast spheres of gas, held together by their own gravity, with conditions becoming increasingly extreme as one moves from the cool surface toward the blazing core. From the physicist's perspective, this equilibrium represents one of nature's most elegant solutions to competing forces. The mathematical equations governing stellar structure describe how the pressure at any point within a star must exactly balance the weight of all the material above it. This creates a smooth gradient of conditions, with temperature and pressure increasing steadily from the star's surface toward its center, where temperatures reach millions of degrees and pressures exceed those found anywhere on Earth. Yet from the contemplative viewpoint, this same equilibrium speaks to something far more profound: the universe's capacity for creating stable, long-lasting structures that can nurture complexity and life. The steady light that has warmed Earth for billions of years, allowing life to evolve and flourish, emerges from this perfect balance between opposing forces. Each photon that reaches our planet carries with it the signature of this cosmic equilibrium, a testament to the patient stability that governs stellar existence. Consider our sun, that familiar star that rises each morning with such reassuring regularity. Within its core, temperatures reach 15 million degrees Celsius, creating conditions so extreme that hydrogen nuclei overcome their natural repulsion and fuse together to form helium. The energy released by this fusion creates an outward pressure that prevents the sun from collapsing under its own immense gravity. This balance has remained stable for approximately 4.6 billion years and will continue for another 5 billion years, providing the steady energy source that makes life on Earth possible. The internal structure of a main sequence star reveals itself as a series of nested shells, each with its own characteristics and role in maintaining the overall equilibrium. In the core, where fusion occurs, temperatures and pressures reach their maximum values. Moving outward, we encounter the radiative zone, where energy slowly diffuses through the stellar material in the form of photons. These photons begin a random walk that can take hundreds of thousands of years to complete, bouncing from particle to particle in an intricate dance that gradually carries energy toward the surface. In stars like our Sun, the outer layers contain a convective zone, where hot material rises and cool material sinks in vast circulation patterns that transport energy more efficiently than radiation alone. This convective motion creates the granular pattern visible on the Sun's surface, a constantly shifting mosaic of rising and falling gas that speaks to the dynamic processes occurring within. The beauty of stellar equilibrium lies not only in its stability, but in its universality. From the smallest red dwarf stars, with masses barely 1/10 that of our Sun, to the massive blue giants that burn with the fury of thousands of suns, the same fundamental principles apply. Each star finds its own unique balance point, determined by its mass, composition, and age, yet all share this common foundation of hydrostatic equilibrium. This equilibrium extends beyond the star itself, influencing the surrounding space through stellar winds and magnetic fields. The steady stream of particles flowing from the star's surface creates a bubble of influence that can extend far beyond the star's visible boundaries, affecting any planets that may orbit within this stellar domain. Within the heart of every main sequence, star burns a nuclear furnace of extraordinary patience, where the universe's most fundamental alchemy unfolds across timescales that dwarf human comprehension. Here, in the stellar core's crushing embrace, hydrogen nuclei dance their ancient dance of fusion, transforming matter into energy through processes so gentle and deliberate that individual reactions occur with the measured pace of cosmic meditation. The proton-proton chain reaction, the sun's chosen pathway to sustaining life, begins with the simplest possible encounter between two hydrogen nuclei. In the stellar core's intense heat, reaching 15 million degrees Celsius, these protons approach each other with velocities that would seem frantic by earthly standards, yet remain infinitesimally slow by the measure of stellar time. The quantum mechanical miracle of tunneling allows these positively charged particles to overcome their mutual electrical repulsion, slipping through the energy barrier that classical physics would deem insurmountable. Hans Bether's Nobel Prize-winning revelation in the 1930s illuminated this stellar secret, showing how stars transform the universe's most abundant element into helium through a chain of reactions so intricate and patient that each proton must wait, on average, billions of years before participating in fusion. This extraordinary patience creates the stellar stability that has allowed life to emerge and flourish across cosmic ages, the gentle constancy that has bathed Earth in steady light for over 4 billion years. In more massive stars, where core temperatures soar beyond 20 million degrees, the CNO cycle takes precedence, using carbon, nitrogen, and oxygen nuclei as catalysts in a more efficient fusion process. These stellar giants burn their hydrogen fuel with greater intensity, yet even here, the nuclear reactions proceed with cosmic deliberation, each individual fusion event a rare and precious occurrence in the vast stellar interior. The quantum tunnel through which protons must pass to fuse represents one of nature's most beautiful paradoxes. Classical physics would predict that stellar cores, despite their intense heat, remain too cool for fusion to occur. Yet quantum mechanics reveals that particles possess a ghostly ability to appear on the far side of energy barriers, allowing fusion to proceed at temperatures far below what classical theory would require. This quantum tunneling enables the gentle nuclear burning that sustains main sequence stars for billions of years, creating the stable energy output that makes planetary systems and life possible. Within our sun's core, approximately 600 million tons of hydrogen transform into helium every second, yet this represents only a tiny fraction of the sun's total mass. The conversion follows Einstein's profound equation E equals mc2, where even the small amount of mass lost in fusion releases enormous energy. 4 hydrogen nuclei, with their combined mass of 6.693, 10 to 27 kilograms, fuse to create one helium nucleus weighing 6.645 and 10 to 27 kilograms. The tiny difference, less than 1% of the original mass, becomes pure energy, powering the sun's luminosity for 10 billion years. The patient accumulation of helium ash in stellar cores creates a gradual change in the star's internal structure, slowly increasing the mean molecular weight of the core material. This subtle transformation causes main sequence stars to brighten gradually over their lifetimes, with the sun becoming approximately 10% more luminous every billion years. This gentle evolution, barely perceptible across human timescales, represents the slow aging of stars as they convert their hydrogen fuel into helium. Neutrinos, those ghostly particles born in stellar fusion, carry immediate news of the nuclear reactions occurring in stellar cores. These nearly massless particles interact so weakly with matter that they stream directly from the stellar interior to space, requiring only seconds to traverse the distance that photons need millions of years to travel. The detection of solar neutrinos by experiments deep underground confirms our understanding of stellar fusion, providing direct evidence of the nuclear processes that power the Sun. The incredible patience of stellar fusion creates the cosmic constancy that enables life's emergence and evolution. Each fusion reaction releases energy that begins a million-year journey from the stellar core to the surface, creating the steady luminosity that has remained essentially constant throughout Earth's biological history. This stellar stability, maintained through the delicate balance of nuclear physics and quantum mechanics, represents the universe's most reliable energy source, the patient nuclear burning that illuminates galaxies and sustains the cosmic processes that create complexity and life. In the vast cosmic theater, where stars perform their billion-year ballets, perhaps no relationship is more profound or paradoxical than the intimate dance between stellar mass and the duration of a star's main sequence lifetime. This cosmic irony unfolds across the galaxy like a gentle meditation on the nature of abundance and longevity, where the universe's most massive and luminous stars burn with such fierce intensity that they exhaust their nuclear fuel in mere millions of years, while their diminutive red dwarf cousins maintain their steady economical fusion for trillions of years, timescales that stretch far beyond the current age of the universe itself. Consider the profound patience of a red dwarf star, perhaps 1/10 the mass of our Sun, glowing with the gentle warmth of a cosmic ember in the galactic darkness. These stellar minimalists, the most common stars in our galaxy, approach their nuclear fusion with the careful economy of cosmic conservationists. Their cores, though hot enough to sustain the proton-proton chain reaction, burn their hydrogen fuel with such deliberate slowness that a single red dwarf, born in the universe's youth, will continue its steady luminosity long after our Sun has evolved through its red giant phase and settled into white dwarf retirement. The mathematics of stellar physics reveals this beautiful relationship. As stellar mass decreases, the core temperature and pressure required for hydrostatic equilibrium also decrease, leading to a more gentle, sustainable rate of nuclear fusion. In the observational realm, astronomers have traced this mass-lifetime relationship across the full spectrum of main sequence stars, from the most massive O-type giants to the smallest M-dwarf stars barely massive enough to sustain fusion. The pioneering work of stellar astronomers in the early 20th century, building upon the foundational observations that led to the Hertzsprung-Russell diagram, revealed that stellar luminosity increases dramatically with mass, roughly as the fourth power of the stellar mass. This means that a star twice as massive as our Sun shines with approximately 16 times the luminosity, consuming its nuclear fuel at a correspondingly accelerated rate. The contemplative mind finds profound meaning in this cosmic relationship. The universe's most spectacular stars, the brilliant blue giants that can outshine entire stellar neighborhoods, live lives of stunning brevity on cosmic timescales. These stellar giants, with masses reaching 50 or even 100 times that of our Sun, burn through their hydrogen fuel with such intensity that their main sequence lifetimes span only a few million years. In the context of galactic evolution, these massive stars are like cosmic mayflies, brilliant and brief, their lives measured in the blink of an astronomical eye. Meanwhile, the humble red dwarfs that populate the galaxy's stellar census represent a different philosophy of stellar existence entirely. Proxima Centauri, our nearest stellar neighbor, exemplifies this patient approach to cosmic longevity. With a mass roughly 1/8 that of our Sun, Proxima Centauri will continue its steady nuclear burning for approximately 4 trillion years, a time span so vast that it encompasses hundreds of times the current age of the universe. When we observe Proxima Centauri's gentle red glow, we witness a star that will outlive not only our Sun, but countless generations of stellar evolution throughout the galaxy. The physical mechanisms underlying this mass-lifetime relationship reveal the elegant simplicity of stellar physics. More massive stars require higher core temperatures and pressures to maintain hydrostatic equilibrium against their stronger gravitational pull. These extreme conditions accelerate the rate of nuclear fusion, leading to higher luminosity but also faster consumption of nuclear fuel. The stellar core becomes a more intense nuclear furnace, converting hydrogen to helium at rates that would power thousands of solar mass stars. This relationship extends throughout the star's structure, affecting everything from the size of convective zones to the efficiency of energy transport from core to surface. Our own Sun occupies a middle ground in this cosmic spectrum, with a main sequence lifetime of approximately 10 billion years. Having already burned steadily for about 4.6 billion years, our Sun represents the patient middle path of stellar evolution. Neither the brief brilliance of massive stars nor the extreme longevity of red dwarfs, but a measured approach to nuclear fusion that has provided stable, life-sustaining energy for the evolution of complex life on Earth. The Sun's mass-lifetime relationship places it in the category of stars that can support planetary systems through the billions of years required for biological evolution to unfold. This stellar mass-lifetime relationship extends beyond individual stars to influence the entire character of galactic evolution. The brief lives of massive stars mean they quickly return their nuclear-processed material to the interstellar medium through stellar winds and eventual supernovae, enriching the galaxy with heavy elements essential for planet formation. Meanwhile, the extreme longevity of low-mass stars means they serve as stable anchors for planetary systems across cosmic time, potentially hosting worlds where life can evolve and flourish over timescales that dwarf the age of our solar system. In the depths of stellar cores, where temperatures soar beyond 10 million degrees and pressures crush matter to densities unimaginable on Earth, an extraordinary journey begins. Each photon born from the nuclear fusion of hydrogen carries within it the essence of stellar energy, embarking upon a voyage that will span hundreds of thousands of years before finally reaching the star's surface and streaming into the cosmic void. This is the patient odyssey of stellar energy, a meditation on the profound timescales that govern the universe's most fundamental processes. Within our Sun's core, photons emerge from fusion reactions only to find themselves trapped in a labyrinth of stellar matter so dense that their path to freedom becomes a random walk of cosmic proportions. Each photon, traveling at the speed of light, might cover vast distances in a straight line. Yet within the stellar interior, it bounces and scatters countless times, its journey resembling a drunkard's walk through the most patient of cosmic mazes. The stellar interior presents layers upon layers of varying density and temperature, each creating its own unique environment for energy transport. In the innermost regions, where fusion reactions occur, the material is so dense that photons can travel only microscopic distances before being absorbed and re-emitted by the surrounding plasma. This process of absorption and re-emission continues endlessly, with each photon gradually working its way outward through the stellar mass, its original gamma-ray energy slowly degrading into lower energy photons through countless interactions. As we move outward from the core, the mechanisms of energy transport reveal the elegant complexity of stellar architecture. In stars like our Sun, the inner regions rely primarily on radiative transport, where photons slowly diffuse through the stellar material like heat spreading through a dense medium. The mathematical beauty of this process lies in its simplicity and inevitability. Energy must flow from regions of high temperature to regions of lower temperature, following the fundamental laws of thermodynamics with patient precision. Yet as we venture further from the core, the stellar interior undergoes a remarkable transformation. At approximately 70% of the Sun's radius, the temperature and density conditions change sufficiently that a new form of energy transport becomes dominant: convection. Here, the stellar material itself begins to move in vast, churning currents that carry energy far more efficiently than the slow diffusion of photons. These convection cells, enormous beyond human comprehension, rise and fall in patterns that dwarf the largest weather systems on Earth. The convective zone presents a fascinating contrast to the radiative interior, where photons once meandered through stellar matter in their random walk. Now entire volumes of plasma rise toward the surface, carrying their thermal energy with them, while cooler material descends to be reheated in the stellar depths. This process creates a dynamic, ever-changing environment, where energy transport occurs on timescales of weeks or months, rather than the hundreds of thousands of years required for radiative transport. Modern heliocosmology has revealed the intricate details of these internal processes, allowing us to peer into the Sun's interior through the study of stellar oscillations. Just as earthquakes reveal the structure of Earth's interior, the Sun's surface oscillations provide information about conditions deep within the stellar core. These acoustic waves, traveling through the solar interior, carry information about temperature, density, and composition, creating a form of stellar archaeology that allows us to understand the Sun's internal structure with remarkable precision. The journey of stellar energy extends beyond the visible surface into the realm of stellar winds and magnetic fields. As photons finally escape the stellar photosphere, they carry with them the story of their long journey from the fusion core. Some of this energy drives the stellar wind, a continuous stream of charged particles that flows outward from the star, carrying mass and angular momentum into the surrounding space. This stellar wind, though incredibly tenuous by terrestrial standards, represents a fundamental connection between the star and its environment, gradually sculpting the interstellar medium over cosmic time. The magnetic fields generated within stellar convection zones add another layer of complexity to energy transport. These fields, created by the motion of electrically conducting plasma, can channel energy in unexpected ways, creating phenomena such as stellar flares and coronal heating. The interaction between convection, rotation, and magnetic fields creates a dynamic stellar atmosphere where energy transport becomes a complex dance of plasma physics and magnetohydrodynamics. Different stellar masses exhibit dramatically different energy transport characteristics. In the lowest mass red dwarf stars, convection extends throughout the entire stellar interior, creating fully mixed stars where nuclear fusion products are distributed throughout the stellar mass. These stars, with their efficient convective energy transport, can sustain nuclear fusion for trillions of years, far longer than the current age of the universe. In contrast, the most massive main sequence stars transport energy so efficiently that they burn through their nuclear fuel in mere millions of years, their luminous surfaces belying the furious pace of fusion occurring within their cores. The contemplation of stellar energy transport reveals the profound interconnectedness of cosmic processes. The light that illuminates our days began its journey in the sun's core during the age of early human civilization, slowly working its way outward through the stellar interior while empires rose and fell on Earth. This perspective offers a humbling reminder of the vast timescales that govern stellar processes, timescales that dwarf human experience yet provide the steady foundation upon which all life depends. In the vast cathedral of our galaxy, where billions of stars burn in patient solitude, we find ourselves contemplating one of the most profound stories ever written in light and time. The main sequence stars that populate our cosmic neighborhood are not merely distant suns burning in the darkness. They are the living chronicles of galactic evolution, each one a chapter in the grand narrative of how our universe has slowly transformed from a simple realm of hydrogen and helium into the complex, metal-enriched cosmos we observe today. When we gaze upon the stars scattered across the night sky, we are witnessing a cosmic library where each point of light represents a different epoch in our galaxy's long history. The ancient, metal-poor stars that drift through the galactic halo carry within their nuclear hearts the memory of a younger universe, when the first generation of stars had only just begun to forge the heavier elements that would eventually become the building blocks of planets and life itself. These population 2 stars, as astronomers have come to call them, burn with a subtle difference in their spectral signatures, their light revealing the chemical fingerprints of a cosmos that had not yet learned to create the rich diversity of elements we see today. The story of stellar populations unfolds like a slow meditation on cosmic time, where each generation of stars has contributed its own verse to the ongoing poem of galactic chemical evolution. In the early universe, when the first stars ignited their nuclear furnaces, they found themselves working with only the simplest ingredients: hydrogen, helium, and trace amounts of lithium forged in the primordial fires of the Big Bang. These pioneer stars, burning bright and massive in the cosmic dawn, lived brief but transformative lives, their deaths in spectacular supernova seeding the interstellar medium with the first carbon, oxygen, silicon, and iron that would eventually find their way into later generations of stars. As we contemplate the patient accumulation of these heavier elements across billions of years, we begin to appreciate the profound interconnectedness of stellar evolution and galactic chemistry. Each main sequence star that burns today carries within its atmosphere the accumulated gifts of countless stellar ancestors, their nuclear alchemy having slowly enriched the galaxy's star-forming regions with the metals necessary for the formation of terrestrial planets and the complex chemistry of life. The Sun itself, our own intimate main sequence companion, represents this cosmic inheritance, its spectrum revealing the presence of dozens of elements that were forged in the hearts of stars that died long before our solar system was even conceived. The metallicity of stars, as astronomers measure the abundance of elements heavier than helium, serves as a cosmic clock, telling us not only when a star was born, but also something about the galactic neighborhood where it formed. Stars with higher metallicity, like our Sun, represent more recent generations that formed from gas clouds already enriched by previous stellar generations, while metal-poor stars speak to us of earlier epochs when the galaxy was still learning to create the chemical complexity we see today. This relationship between stellar composition and cosmic time creates a beautiful symmetry in our understanding of galactic evolution, where the patient burning of main sequence stars both drives and records the slow transformation of our cosmic home. The study of stellar clusters provides us with perhaps the most elegant natural laboratories for understanding these stellar populations and their relationship to galactic evolution. Globular clusters, those ancient spherical collections of hundreds of thousands of stars, preserve for us snapshots of the galaxy's youth, their population 2 stars, all born at roughly the same time from the same primordial gas cloud. When we observe these clusters through our telescopes, we are essentially looking back in time, seeing main sequence stars as they existed when our galaxy was young, and the universe itself was only a fraction of its current age. In contrast, the open clusters scattered throughout the galactic disk tell us the story of more recent star formation, their population 1 stars enriched with the metals created by generations of stellar nucleosynthesis. These younger stellar associations, often still embedded in the nebula material from which they formed, show us stellar populations that have benefited from billions of years of galactic chemical evolution. Their main sequence stars burning with the accumulated wisdom of cosmic time. The contemplation of stellar populations leads us naturally to consider the profound patience required for galactic evolution to unfold. The process by which our galaxy has slowly enriched itself with heavier elements represents one of the most gradual transformations in the universe, playing out over timescales that dwarf not only human experience, but even the lifetimes of the longest-lived main sequence stars. Each generation of stars must live out its complete main sequence lifetime, contribute its processed material to the interstellar medium, and allow that material to be incorporated into new star-forming regions before the next chapter of galactic evolution can begin. This cosmic recycling process, driven by the patient burning of main sequence stars and punctuated by the dramatic deaths of more massive stars, has created the chemical diversity that makes our modern universe possible. The calcium in our bones, the iron in our blood, the oxygen we breathe, all trace their origins to the nuclear furnaces of stars that burned on the main sequence long before our solar system existed, their patient fusion processes slowly building up the elements that would eventually become the foundation of terrestrial worlds and biological complexity. In the vast cosmic theater, where stars perform their billion-year ballet of nuclear fusion, perhaps no relationship is more profound than that between these stellar beacons and the worlds that orbit them. The habitable zone, that gentle region of space where liquid water can exist on planetary surfaces, represents one of the universe's most delicate and beautiful arrangements, a cosmic Goldilocks zone where conditions are neither too hot nor too cold, but just right for the chemistry of life to unfold. Around every main sequence star, this invisible sphere of possibility extends outward from the stellar surface, its boundaries determined by the patient, steady luminosity that has remained constant for billions of years. For our Sun, this habitable zone encompasses a region stretching from roughly the orbit of Venus to just beyond Mars, with Earth positioned in that sweet spot where stellar radiation provides exactly the right amount of energy to maintain liquid oceans beneath protective atmospheric blankets. The beauty of this arrangement lies not just in its current state, but in its remarkable stability across cosmic time. Immaculate sequence stars burn their hydrogen fuel with such measured patience, they provide the consistent energy output that planetary atmospheres require to maintain their delicate balance. Unlike the violent variability of younger stars or the dramatic changes that accompany stellar death, main sequence stars offer their planetary companions the gift of predictability, a steady, reliable source of energy that changes so slowly that life has time to adapt and evolve. This stellar constancy becomes even more remarkable when we consider the intricate dance between star and planet that enables habitability. The stellar radiation that bathes planetary surfaces doesn't simply provide warmth. It drives the complex atmospheric chemistry that maintains the greenhouse effect, powers the water cycle, and creates the dynamic weather patterns that distribute energy around planetary surfaces. On Earth, this stellar energy has sustained the hydrological cycle for nearly 4 billion years, lifting water from the oceans, carrying it across continents as clouds, and returning it as the rain that nourishes all terrestrial life. The relationship between stellar properties and planetary habitability reveals itself most clearly when we examine the diverse family of main sequence stars. Around the smallest red dwarfs, those patient stellar citizens that will burn for trillions of years, the habitable zone lies much closer to the star. Planets in these zones often become tidally locked, with one hemisphere permanently facing their star while the other remains in eternal darkness. Yet even in these extreme conditions, the steady energy output of red dwarf stars could potentially support atmospheric circulation patterns that distribute heat around the planet, creating conditions where life might find a way to flourish. The more massive main sequence stars, burning brighter and hotter than our Sun, push their habitable zones farther outward. These stellar giants, though they will exhaust their hydrogen fuel more quickly, still maintain their main sequence stability for millions or billions of years, time enough for planetary systems to form and evolve. Around such stars, the habitable zone might encompass regions where gas giant planets could harbor habitable moons, their surfaces warmed by stellar radiation, while their interiors remain heated by tidal forces from their massive parent planets. The discovery of thousands of exoplanets around main sequence stars has revealed the extraordinary diversity of planetary systems that can form around these stellar beacons. Some planets orbit so close to their stars that their surfaces are molten rock, while others circle so far away that they remain frozen worlds of ice and stone. Yet between these extremes lies that precious habitable zone. And increasingly, we find planets residing within these regions of possibility. The habitable zone concept, however, extends beyond simple temperature considerations. The stellar radiation that defines these zones also influences planetary atmospheric evolution in profound ways.